Hi guys and girls, video here on critical regions. This one is going to be based on binomial distribution. It's kind of the same process for things like normal distribution and all that kind of thing as well. But I will be using binomial distribution in this. So a critical region is basically the cutoff that is needed to say, well, anything beyond this cutoff will result in you accepting your alternate hypothesis. Okay, so let me just note that down. So critical region is the cutoff value beyond which H0 is rejected. And then whether it's a greater than or a less than, just, will depend whether you need to be above it or below it. So, in terms of your graph, what you'll be finding is your significance level will be given to you in a question. So, if I do that, for instance, the probability here has to be your significance level. This part is your critical. Well, sorry, that's worded badly. This point here, that is your critical value. Okay, that kind of makes sense. And then often it's talked about in terms of a rejection region or an acceptance region. So this is your acceptance. So you accept H0. And then in this section is reject H0. Right, it could be at the top end like I've shown here, it could equally be at the bottom end. It depends on the scenario you're trying to test. We've got a couple of examples for you. So the first one, a coin is tossed 200 times. So we know that n is 200 in our binomial distribution. It's a coin, so the probability of landing on heads, we've mentioned heads there, is half. So our distribution, x is distributed binomially with 200 trials and a probability of a half. How many heads will be needed in order to say that the coin is biased at the 1% significance level? So what we're trying to find is the value here where this area is 1%. Right, it's a one-tailed hypothesis because, it is a one-tailed hypothesis because you want it to be biased, and because there's only two outcomes, if you've got more heads than tails, then it's biased towards heads. You could have it as less than, and then it would be biased towards tails, but it's a 50-50 coin, so it doesn't matter. Okay, so we need to do our usual, state our null hypothesis. So the probability is going to remain at a half. The alternate hypothesis is going to be that it is greater than a half. The thing we are measuring is the proportion. If you can hear a cat bell, just ignore her. She's playing silly this morning. Proportion of heads in 200 rolls. X is heads. And what else do we need? Oh, we are trying to find the probability of X being greater than a value, let's call it K, has to be at least 0.01. Right, if it's bigger than 0.01, then we're not in that shaded region. So, let's give myself some more space. Right, we can't do greater than in our calculator, so we have to do 1 minus x is less than or equal to k. And if that's the case, then this has to be at least 0.99. And to effectively kind of take away one from both sides and flip the sign. Okay, so this is where your calculator is going to come in really handy. So you go to your calculator functions and you try out some values. That's it. So if I was to sub into mine, I'm just going to set up a little and say that if k is, now there's 200 values, so in theory we know it's going to be more than 100. So if we test out, I don't know, 110, if we test out 110, the probability is 0.9313. Okay, that's not as high as I need, so let's say 115. That is 0.9859. Pretty close, so I'm just going to go up one more. That is 9903. So that's the first one that's going to be above our 0.99 that we need. So my critical value, critical value is 116. So if there are 116 or more heads out of our 200 throws, then our dice is biased towards heads. Okay, another example. Let's see if we can get all that on the page. Oh, there we go. So a score states that 40% of students get A's and A stars. Okay, so do I know how many? I've missed something off the question. I've just looked up my notes. The sample is 150 students. Okay, so N is 150. And the probability of them getting an A star, A or A star, is 0.4. So X is distributed binomially with 150 and 0.4. So a new scheme has been introduced and they want to know if it's improved. What's the critical region for critical value, the number of A's and A stars at the 5% significance level. Okay, so H0, no change, so stays at 0.4. Alternate, we want to know that it's improved, so it's got to be greater than 0.4. P is proportion, spell proportion right, of A/A star in 150 students. And, sig level. I didn't write down my sig level last time, did I? Sig level is 5%. And we are finding the greater than K again. So we're still going to have to do 1 minus X is less than or equal to K in our calculator. And that's got to be less than 0.05. Which means the probability of less than or equal to K has to be at least 0.95. And again, we're going to go to our calculator. So if it was 40% generally get A stars, 40% of 150 is 60. So we would expect it to be 60, so we're going to want to go for more than 60. So I'm going to go 70. 70 in our calculator, that comes out at 0.9591. Oh, okay. So that's already greater than 0.95 that we want, but I don't necessarily know whether it would have hit. That's definitely the first one, if you like. So let's test 69 just to make sure. Okay, that comes out at 0.9425. So I just hit a lucky guess. So that is the first one that is above 0.95. So my critical value, so at least 70 A/A stars are needed to say there has been an improvement. Oh Lord, there we go. Improvement. Okay. It's fairly simple. It's set out your normal binomial hypothesis test. Figure out what you've got to be greater than. Use your calculator and do a bit of a trial and improvement to find the first number that is above that significance level. There you go. Not terribly difficult, hopefully. Anyway, catch you later. Bye.